Why might your memories not be entirely real? Imagine your childhood, those once vivid pictures in your mind. Could these stored fragments of the past be nothing more than a story constantly rewritten, or even fabricated? The truth might be far more unsettling, yet far more fascinating than simple forgetfulness. I hope the next 40 minutes take you on a mind-bending journey through the past and future, ultimately revealing its startling connection to the universe's deepest secrets. At the heart of it all lies a potentially revolutionary way of thinking about the nature of time itself. How we perceive and store the past is intrinsically linked to this most fundamental dimension of the cosmos, especially when we try to understand our own existence by combining our notion of memory with Einstein's description of space-time. This is sure to refresh your understanding of time. Let's start with the simplest breakdown to make it easier to grasp. In daily life, time is an indispensable part of existence. It governs our birth, aging, sickness, and death, even the changes we observe in the world. But have you ever wondered, what exactly is time? Is it merely a way for us to measure the past, present, and future, or is it something woven into the very fabric of the universe? At first glance, time is you looking at a clock, knowing it's midnight and time to sleep. But the deeper scientists delve into studying time, the more complex it becomes. Modern physics tells us time is not an independent entity, not something that ticks autonomously on its own. Time is intricately connected to space. Space and time are not separate dimensions, but a unified whole. Imagine space as an invisible membrane, stretching infinitely in all directions. It's not a tangible film you can touch, but a smooth, serene structure carrying everything in the universe. Stars, planets, galaxies, even the light traveling between them. Now imagine this membrane represents not just space but also time. Together, they form what scientists call space-time, a single, unified structure forming the foundation of the cosmos. We typically think of space as your up-down, left-right, and forward-backward, and time is yesterday, today, tomorrow. But in reality, they are not separate. They are two aspects of a deeper reality, interwoven like the warp and weft on the same piece of fabric. The concept of space-time, first proposed in the early 20th century, marked a monumental shift in how scientists understood the universe. Before that, space and time were seen as independent and absolute. But then Einstein completely changed this view. In his general theory of relativity, Einstein proposed that space and time are not fixed or rigid. They are dynamic and flexible. Space-time can stretch, compress, bend, and even ripple. It reacts to the presence of matter and energy. In fact, gravity itself is not a force in the traditional sense, but rather the result of space-time bending due to mass. To understand this, imagine stretching a rubber sheet flat to represent space-time. Place a heavy bowling ball in the center. The sheet will sag under the weight, bending the surrounding area. If you roll a small ball on the sheet, it will curve towards the heavier ball. This is how Einstein viewed gravity. Massive objects bend space-time. This bending affects not just space. Since space and time are part of the same structure, when space bends, time bends along with it. In Einstein's model, time does not pass at a fixed rate. There is no universal rhythm across the cosmos. It is shaped by the same conditions that shape space. So, in Einstein's relativity, time doesn't have built-in labels like past, present, or future. These are words we use to describe our experience, but they don't exist in the physics itself. The equations of general relativity don't point to this as the past or that as the future. They simply describe how time behaves, how it stretches and bends together with space. Einstein's model treats time as a dimension, just like the three dimensions of space. In space-time, you add a fourth coordinate, time. The three dimensions of space plus the one dimension of time together define the where and when of something in the universe. While in daily life it seems we can move freely in any spatial direction, and we feel we live in now and move towards the next, in the mathematics of general relativity, all moments of time seem to simply exist. The theory doesn't tell us which moment is now, nor does it favor the past or future. It just lays out the structure of space-time all at once. This is where it starts to get mind-bending. If time doesn't flow, if all moments exist similarly to how all locations exist in space, then all our experiences also exist in time. We experience them in sequence, but they were already present in the fabric of the universe. Einstein himself said, "The distinction between past, present, and future is only a stubbornly persistent illusion." He wasn't saying time is unreal, but that our experience of its flow might be a creation of our minds, not an inherent property of the laws of nature. The question arises, if this is true, why do we remember the past but not the future? Why does a shattered cup stay shattered and not spontaneously reassemble? If physics doesn't favor any moment, why does time feel like it's always flowing forward? Where does this sense of direction come from? This is the classic problem of the arrow of time. While Einstein's equations treat time as just another coordinate like space, our everyday experience insists that time has a definite direction. It flows from the past to the present, never reversing. We are born, grow, age, and ultimately die, a process that cannot be reversed. There is a profound one-wayness to the world we live in. To explain this, scientists turn to the second law of thermodynamics, entropy. Things naturally move from order to disorder, from neatness to chaos. For example, you drop an egg, the shell shatters, the yolk spills out. This is an increase in entropy. For the broken egg to jump back into your hand and reassemble into a whole egg is incredibly unlikely, theoretically not impossible, but the probability is so small it essentially never happens in reality. This direction from order to disorder gives time its arrow. Entropy applies to everything, from stars burning out to ice melting, to the expansion of the universe. The increase of entropy gives us the feeling of before and after. It imparts a directionality to time, even though the fundamental laws of physics themselves have no such arrow. Here's a simple analogy. The words on page 10 of a book are no more or less real than the words on page 50. They exist in the book simultaneously, but we read from front to back. Similarly, all moments exist in the book of the universe's space-time, but entropy is how we experience them in one direction. If you filmed an egg falling and played it backwards, it would look strange because it violates that deeper rule of increasing entropy. That's how we can tell if a video is playing forwards or backwards. We recognize the arrow of time. Now things get even more fascinating. The laws of physics don't actually say the egg can't unbreak. They just say it's extremely improbable, to the point of not happening. But the equations work just as well running backwards. This means the direction of time isn't baked into the equations. It comes from the arrangement of things, from the quirky way entropy works. This suggests the rules governing the universe are more flexible. The future and past might not be as distant as we think. But to explore these possibilities deeper, we must ask a bigger question. If time can bend and entropy gives it direction, is there any way to travel through it? Let's start by trying to jump to the future, and there are some famous, successful real-world cases. A notable case of significant time dilation from spaceflight, effectively traveling to the future, is Russian cosmonaut Sergei Krikalev in October 2005. Over nearly 20 years, he spent a total of 803 days, 9 hours, and 39 minutes in space. He wasn't just a cosmonaut. Technically, he was a time traveler to the future. Yes, you heard that right. On the space station, he was moving at about 27,600 kilometers per hour. According to special relativity, the faster you move relative to someone at rest, the slower your time passes. Over his 803 days in space, this difference accumulated to roughly 20 milliseconds. So when he returned, compared to if he had never left Earth, he was strictly speaking in the future. He didn't go into the future faster than us. Rather, we moved through time faster than he did. This is called time dilation, a real, experimentally confirmed effect. The equation explaining it is the time dilation formula from special relativity. We won't dive into the math, just understand the meaning. When your speed approaches the speed of light, simply put, The faster you go, the slower time passes for you. While negligible in daily life, imagine boarding a ship traveling at 99.9% the speed of light. For you, it might feel like a year passes, but when you return to Earth, decades have passed there. People you knew would have aged, perhaps even passed away. From your perspective, you aged 1 year. From Earth's perspective, you leaped into the distant future. Your own clock slowed down so much that you traveled through time without feeling anything unusual. Simple analogy, I'm on Earth watching a movie at normal speed and you're watching the same movie, but in slow motion. The longer you watch, the more out of sync you become with me. Eventually, when my movie ends, you might only be halfway through. That's what happens when you move near light speed. Your time crawls while the rest of the universe rushes by around you. Besides speed, according to general relativity, gravity is actually the curvature of space-time itself. The more massive an object, the more it warps the space and time around it. The closer you are to that massive object, the slower your time passes. This is called gravitational time dilation, one of the most astonishing parts of Einstein's theory. Remember in Interstellar, when Cooper lands on the planet orbiting near the gargantuan black hole? The black hole's gravity stretches space-time so extremely that on that planet, time is almost at a standstill compared to Earth. Every hour they spend on the surface equals 7 years back on Earth. When the crew finally returns to their ship, only hours have passed for them, but a crewmate left on the mothership has aged 23 years, simply because they were close to a black hole where time runs slowly. While it sounds fantastical, gravitational time dilation is an observable phenomenon, even in everyday context, though the effects are far less dramatic than with a movie's supermassive black hole. In the 1970s, scientists tested gravity's effect on time by taking 2 highly precise atomic clocks to different altitudes. One clock stayed at sea level, the other was taken to a mountain top about 2,300 meters high. After 11 days, comparing the clocks revealed the one on the mountain ran slightly faster. This is a direct result of gravitational time dilation. The reason, the mountain clock is farther from Earth's gravitational center. The higher the altitude, the weaker the gravitational field, and thus the less warping of space-time. The difference between the clocks was tiny, mere 100,000ths of a second, but measurable with the technology of the time. Besides traveling near light speed or a giant black hole, there's another way to go to the future, the concept of a warp drive. In 1994, physicist Miguel Alcubierre proposed a theoretical idea called the Alcubierre drive, which caused a sensation in the scientific community. Using the mathematics of general relativity, Alcubierre showed that if you could shape spacetime in the right way, you could create a region of space that moves faster than light relative to the external universe. Inside the bubble, the traveler's time would pass normally. Outside, however, the ship could cover distances that would take light millennia in a very short journey. In other words, instead of making the ship move faster and faster through space, make the space around the ship move. Normally, we think of travel as propelling through space like a car on a highway. But in Einstein's general relativity, space and time aren't just an empty stage where events happen. They're more like a stretchable fabric that can be warped, bent, and even rippled. If you could control this fabric, you wouldn't have to move through space in the conventional way at all. You could ride a patch of space that's itself moving. This is what we often call a warp drive or curvature drive, creating a bubble of space around the spacecraft. In front of the bubble, space contracts. Behind it, space expands. The spacecraft inside remains completely stationary relative to its surrounding space. It's not moving at all. But the bubble itself would surf through the cosmos. Because the ship isn't technically moving through space, it could theoretically travel faster than light without breaking any physics laws. It's like surfing. You and the board are stationary, it's the wave pushing you. This isn't just faster than light travel, it's also travel to the future. The reason is that time inside the warp bubble behaves differently. You might experience only months or years, while centuries could pass outside the bubble. Imagine leaving Earth in 2100. arriving at another star after what feels like a year to you, only to find Earth's calendar reads 3100. You've effectively jumped 1000 years into the future while aging only a year. Another important detail, you wouldn't feel any acceleration inside the warp bubble. Theoretically, you wouldn't even need massive shields against interstellar dust. They'd just float by peacefully as the external universe whizzes past at incredible speeds. But to actually make this work would require something called negative energy, or exotic matter, a type of energy that behaves opposite to normal mass and energy, producing repulsive rather than attractive gravity. So far, negative energy is purely theoretical. We know it can exist in tiny amounts in quantum fields, like in the Casimir effect, but we've never been able to create or harvest it in usable quantities. While labs like NASA's Eagle Works have researched the idea, mastering such technology remains a distant prospect. Another idea for traveling to the future involves white holes. White holes also come from the math of general relativity. They are the exact opposite of black holes, where a black hole only lets things in and not out. A white hole is an object you can never enter because it constantly pushes everything away. Some scientists propose white holes might be connected to black holes via wormholes. Setting aside the issue of surviving a trip through a black hole, you might emerge from a white hole at the other end. Due to the extreme warping of spacetime inside the black hole, when you emerge from the white hole, you could find yourself in a distant future, far beyond the era you started in. Imagine entering a black hole in 2025 and emerging from a white hole in 4025. From your perspective, only minutes or hours might have passed, but thousands of years could have passed on Earth. However, a white hole would be a one-way time machine to the future with no return trip allowed. The catch: white holes are purely theoretical for now. We've imaged black holes, but white holes have never been observed. Another way to go to the future is simply to freeze yourself and wait. While it sounds humorous, it seems the simplest method. Sleep for decades, centuries, or longer, and when the world's technology matures, you can be thawed and start life anew in a future era. The current bottleneck is safe revival, so whether you'd make it to the day of awakening is unknown. The odds of success may be low, but it's also an experiment in hope, a gamble betting that the future will find a way to revive you. Many ideas for jumping to the future have been proposed, but what about going backward in time? That sounds impossible. Yet, as you delve into the strange world of physics, you find hints that it just might be possible. While there are many movies about going back in time, reality isn't science fiction, but this is something physicists have seriously considered. Is there really a way to return to the past? Can time be treated like space, where finding the right path lets you move not just forward, but backward? First, let's be clear. Real-world ideas for going back in time are far more difficult and complex than going to the future. But general relativity actually allows for some wild possibilities. One of the most intriguing ideas is the concept of wormholes, tunnels hidden in the fabric of spacetime that could connect not just distant points in space, but also distant points in time. Again, take Interstellar. The film uses incredible ideas, but the physics behind them is closer to real science. When Cooper falls into the gargantuan black hole, he doesn't just experience extreme time dilation. He ends up in a tesseract, a strange higher dimensional space where time is no longer linear. Cooper can see past, present, and all versions of a room stacked like a deck of cards, spread across dimensions. In that moment, Cooper isn't just traveling through time, he's shaping it. And because his daughter solves the equation, future humans created the Tesseract and sent him back to save her, a perfect closed loop across time. The entire process doesn't break the past or create a paradox. He isn't changing history in the sense of creating a new timeline. Rather, everything he does inside the Tesseract has already happened. He was always the one who sent the messages. He just didn't know it before entering the Tesseract. The future and the past are entangled in a way that keeps everything consistent. This idea aligns with a concept in physics called a closed time-like curve, a loop where time circles back on itself, and events are self-consistent. It means the future and past can influence each other without breaking causality. You might think, that's not physically going back in the past. The physically possible answer might be wormholes. Theoretically, wormholes are shortcuts through space-time. Instead of traveling the long, flat route through space, you slip through a tunnel and pop out somewhere far away, perhaps even at a different time. Imagine the universe is a giant sheet of paper. If you fold the paper and poke a hole through it, two distant points touch. You can jump from one place to the other instantly. That's the basic idea of a wormhole, what physicists call an Einstein-Rosen bridge, a bridge connecting 2 points in spacetime. And depending on how you set it up, it could let you travel not just through space but through time as well. Now we're getting closer to answering the opening question, but things are also getting wilder. If one end of a wormhole is made to move through time differently than the other end, could become a real time machine. You could enter one mouth and exit the other at a different time, either in the future or the past. One way is to move one mouth of the wormhole at near light speed, like towing one end with a rocket ship. Due to special relativity, time for the moving mouth would slow down relative to the stationary one. When you bring them back together, the two mouths are out of sync. Walking into the stationary mouth, you might exit the moving mouth in the past and vice versa. So, what determines whether you jump to the past or future through a wormhole? It all depends on how the two mouths are treated. If the moving mouth experiences less time because it traveled near light speed or stayed near a massive object like a black hole, it could be younger than the stationary mouth. Walking from the older mouth to the younger one sends you to the past. The reverse shoots you to the future. Think of it like an escalator where one side moves faster than the other. Depending on which direction you step, you either get ahead or fall behind. In a wormhole, going the right way might land you in yesterday, another way might drop you in tomorrow. But there's a limitation. You can only go back to a time after the wormhole was initially created. You can't use it to visit the age of dinosaurs unless that wormhole has existed that long. Science fiction often focuses on traveling forward in time because it seems easier, but going backward is where it gets really tricky and interesting. A wormhole could, at least in theory, let you go back to your own past and meet your younger self. Of course, there are huge problems. First, wormholes need something called exotic matter to stay open. Ordinary matter would collapse under gravity. Exotic matter must have negative energy density, essentially pushing outward against gravity's pull to hold the tunnel open. No one has found exotic matter, but physics allows its existence. Quantum effects suggest negative energy can exist. We just don't know if it can exist in the right amounts or be stable enough for use. Second, wormholes need to stay stable. Even tiny disturbances, like a radiation particle or tidal forces, could cause it to collapse before anyone passes through. If a wormhole closes while you're halfway through, the outcome is unthinkable. At this point, paradoxes inevitably arise. If you could go back through a wormhole, you could do things like prevent your grandparents from meeting or send a message to your past self that changes your own decisions. The most famous is the grandfather paradox. Nevertheless, from a purely physics perspective, wormholes don't automatically forbid time travel. General relativity allows for the existence of closed time-like curves, paths that loop back on themselves. This means under the right extreme conditions, the universe might permit returning to the past without immediately blowing up reality. If traversable wormholes currently sound impossible, another strange idea lurks in Einstein's math, the closed time-like curve itself. CTCs are even weirder because you don't necessarily need a wormhole to create them. The shape of spacetime itself might allow time loops. A CTC is essentially a loop in spacetime where time doesn't flow in a straight line but curves in such a way that an object or person traveling forward could eventually circle back to a point in their own past, forming a closed path. This means if you followed a CTC, you could theoretically return to a moment in your own past without violating physical laws, because the object or person is simply following a loop back to its starting point in time. idea was first proposed by the famous mathematician Kurt Gödel in the 1940s in a model of the universe, a solution to Einstein's general relativity equations describing how mass and energy warp spacetime. These equations allow for the possibility of closed paths in spacetime. Unlike earlier described time travel to the infinite future, CTCs as closed loops would allow an object to trace a path through spacetime and end up returning to the moment it started, despite having experienced the journey through time. Such a path wouldn't violate the laws of relativity, but it would indeed create paradoxes, most famously the grandfather paradox. For CTCs to exist in reality, certain conditions are needed. First, the spacetime forming the CTC must be extremely curved or twisted, which could occur around rotating black holes like Kerr black holes. The immense gravity around such objects might produce the kind of closed time-like curves described by the equations. Theoretically, if you entered such a black hole, you could follow the curves of spacetime in a loop and come back to a time before you entered. However, this is purely theoretical. No one has actually observed this phenomenon. Yet all these ideas about going back in time run into a big problem: the grandfather paradox. Imagine you build a time machine, go back to when your grandfather was young, and accidentally prevent him from meeting your grandmother. Maybe you just bump into him, making him miss a date. Now, if they never met, your parents wouldn't be born. If your parents weren't born, you wouldn't be born. But if you were never born, who changed the past? Later, scientists tried to resolve this without abandoning the dream of time travel. One idea comes from quantum mechanics, specifically the many worlds interpretation. In this view, every action you take creates a new, independent universe. So if you go back and stop your grandfather, you don't erase your original timeline, you only create a new timeline where you never existed. But your own timeline remains intact. It's like duplicating a file on a computer. You haven't deleted the first file, just made a new, different version. This sounds clean. The timeline you came from still exists. But the issue is, it means you can never truly change your own past. You can't fix your mistakes or save someone who died in your world. You'd only affect a copy, not your real history. Even if the many worlds interpretation helps patch the grandfather paradox, it can't solve everything. There's also the bootstrap paradox, which is even stranger. Suppose you take a copy of Beethoven's symphonies back in time and give it to the young Beethoven. He copies them down and becomes famous. But where did the symphonies come from? You got them from Beethoven, but Beethoven got the music from you. There's no original moment of creation. It just cycles forever through time. The bootstrap paradox disrupts the basic concept of causality. Usually, something happens because something else caused it. But here, cause and effect seem to create each other. It's like standing between two mirrors seeing infinite reflections, but unsure which one started it all. Scientists haven't found a satisfactory solution yet. Some think if time travel is possible, these closed loops are just how the universe works. Others think perhaps these paradoxes prove that true backward time travel simply cannot happen. Then there's the predestination paradox, an even more bizarre twist. What if everything you do to try to change the past actually causes it to happen? For example, you learn a terrible disaster will occur in the future, so you build a time machine to stop it. But when you go to the past, you make a mistake and accidentally cause the very disaster you wanted to prevent. You're not the hero, you're the reason it happened. Every paradox forces us to confront a harsh truth. Even if physics allows travel to the past, the way the universe is structured might prevent you from changing anything meaningful. Perhaps history is like cement. You can leave a footprint, but you can't truly reshape the whole sidewalk. Or if the multiverse is real, then every trip to the past just branches into a new world, leaving your original timeline untouched but creating countless new ones. Either way, there's no perfect solution. Every answer seems to raise more questions. Every patch creates new cracks. Time travel seems impossible for good reason. Paradoxes hit us from every angle, making the idea of going back and changing history like trying to unscramble an egg. The universe just doesn't seem built for it. But if we combine all the theories, we might piece together something powerful enough to bend time at will. Let's start from the core, the power source. Traveling through time isn't like driving on a highway. You're not just moving through space. You're tugging at the very fabric of space-time itself, trying to fold it, warp it, and push yourself through it. This requires unimaginable energy, far beyond anything humanity has ever harnessed. A rotating black hole, called a Kerr black hole, doesn't just warp itself, it drags the surrounding space-time around with it, a peculiar effect called frame dragging. Imagine it as a massive tornado made of gravity itself. If you could somehow fly close enough without being crushed, you could ride this vortex and loop around in time. The idea is that near a rotating black hole in a region called the ergosphere, space-time is warped so severely that moving forward in the conventional way is no longer your only option. If you choose the right path, the right orbit, you could theoretically return to your own past. The black hole acts like a cosmic dynamo, a generator twisting time. Of course, no known material could survive near a black hole's event horizon under such extreme energy. But in our hypothetical time machine system, imagine a massive space station orbiting the black hole at just the right distance. Immense magnetic fields would extract energy from plasma streams, converting chaos into something usable. With energy, you need to create the actual time passageway. This is where the space-time ring comes in. Imagine stirring a large bowl of honey. At first, the honey just swirls, but if stirred fast enough, the middle part starts to fold in on itself, forming little vortices and loops. This is what we're trying to do to space-time itself. Stir it so fast with immense mass and energy that it begins to fold, forming closed loops in time. These are the closed time-like curves we discussed. A model for this idea comes from the Tipler cylinder, proposed by Frank Tipler in 1974. This hypothetical object envisioned an infinitely long cylinder made of incredibly dense matter, rotating at near light speed. Around this cylinder, space-time would warp so violently that time loops might form. Of course, there's a problem. An infinitely long cylinder doesn't exactly fit in our universe. We can't just build a never-ending spinning rod in space. So any real version would have to be finite, which is tricky. A finite Tipler cylinder wouldn't work perfectly on its own. You'd need extra help, like exotic matter or extreme precision in construction, for the loop to form without collapsing. In our machine's version, imagine a giant glowing ring, not infinite but massive enough and spinning fast enough that the surrounding spacetime begins to twist. This ring would glow from the energy coursing through it, like a giant hula hoop made of starlight, spinning at super speeds. Holding it together would require materials we don't currently possess, something tougher than any known metal or composite. Perhaps future technology utilizing exotic states of matter or harnessing the power of cosmic strings. Theoretical objects thinner than an atom but heavier than a mountain could achieve this. It's a monumental task, but it's the scaffolding we'd need to shape the river of time. Even with this ring, we're not done. You still have to carve a path through the warped spacetime. This is where wormholes come in, but wormholes are unstable. To keep one open, you need exotic matter, something with negative energy density. Negative energy exists. For example, in the Casimir effect, two metal plates brought extremely close together in a vacuum experience a tiny but measurable force pulling them together, caused by negative energy between them. This isn't exactly the exotic matter we need, but it hints the universe might allow it. If we could create or collect enough negative energy, we could inflate a wormhole's throat wide and sturdy enough for a traveler, or even a ship, to pass safely. But how would you know where you're going? This is where navigation becomes crucial. Ordinary GPS satellites work by sending timing signals from space. Your phone or car receives these, calculates the time it took to arrive, and pinpoints your location. But in time travel, everything is moving. Earth rotates and orbits the sun orbits the galaxy moves through the universe. If you travel just minutes into the future or past without accounting for this, you might end up floating in empty space where Earth used to be. The solution might be quantum entanglement. Entangled particles remain connected no matter how far apart. If we could entangle clocks or particles at specific spacetime coordinates, they could act as anchors, providing travelers a way to lock onto a location and time. Work by Anton Zeilinger on quantum teleportation and Pan Janeway's experiments with quantum satellites show quantum entanglement can be maintained over large distances. Perhaps one day, a quantum entanglement network could serve as the ultimate map for time travelers, a web of unbreakable beacons spanning the cosmos. It would be like a GPS for time, except instead of satellites, you're using particles woven into the fabric of space-time itself. With today's technology, all this seems like armchair theory. But who can say that in a few hundred or thousand years, humanity couldn't build a time machine? A few centuries ago, humans dreamed of flying like birds or covering thousands of miles in a day, fantasies that are now our daily reality. Isn't that miraculous? Similarly, if a future civilization could harness the behavior of space-time, building a machine that rides the river of time would be, to us now, pure magic. Now back to our core question. How do you know your memories are all real and reliable? Based on all our analysis, if time travel were ever realized, then the past could be influenced by the future. This means, are those fragments of the past in your mind really how they originally were? Or have they been quietly edited? Or are they even implanted memories of events you never experienced? Well, the mind-bending journey ends here. Despite time travel being full of mysteries, traps, and impossibilities, the chase is not without value. In trying to unravel the mystery of time, we push the limits of physics, engineering, and imagination. Perhaps human dreams are the very essence of science. In the vast universe, how can a civilization that has only entered the technological age for a few hundred years possibly comprehend the advanced technologies that might exist in the cosmos? As history has shown, given enough time, humanity always finds a way to turn imagination into reality. With this curiosity, with this imagination, I wish you a good night's sleep. Good night. All right, my friend, our journey through the mysteries of the universe pauses here for tonight. Now let us press pause together. Gently set aside all thoughts and wonder, and simply be present in this moment of quiet. From here, my voice will gradually fade away, replaced by a silent tapestry woven by the cosmos itself, along with a specially tuned frequency of 432 Hz. Many believe this frequency resonates with nature's own rhythm, aligned with the pulse of the earth and the essence of life, softly soothing the waves of the mind, and guiding body and spirit into deep tranquility. Now, settle into your most comfortable position. Slowly close your eyes, or let your gaze rest gently upon the starlit canvas. May you release the weariness of the day, allowing your awareness to drift on these soothing sound waves, floating freely in a boundless sea of calm. Good night and sweet dreams, until we meet again among the stars.